In this third video segment, we are looking at the control of legged robots. When talking about control, we have to distinguish between static and dynamic locomotion. Static locomotion means that we are statically stable, so the body weight is continuously supported by multiple ground contact, by three ground contact that make a extended support polygon, and the center of gravity stays within the support polygon. That means even if we freeze all the joints, we immediately stop the system, the center of gravity remains within the support polygon and the system does not fall over. This is the way how system used to be controlled when we were having only position controlled systems that were moving relatively slow, statically stable. I wouldn't say that this is the type of research that people are doing right now. The second type of gates we have to look at and type of control we have to look at is dynamic walking. Dynamic walking means that we are having only few points in ground contact. There might be just single point contact, no ground contact, or lines of ground contact. That means that if we stop the robot, it will just fall over. So it has to actively balance, otherwise it cannot stand. These gates are typically fast, they're energetically efficient, but they're much more demanding for control and actuation. In the first part of this video segment, I will discuss the statically stable part. In this lecture, we looked at 4 different control concepts. The first thing we looked at was kinematic control. Kinematic control means that we were planning a position motion and we had high gain joint position trajectory following. The second thing we looked at was impedance control with joint space inverse dynamics. So in other words, we included kind of PD feedback gains in every joint, like spring damper element for every joint, and did some model-based compensation, so low gain joint feedback plus model compensation. The third control method we looked at was support consistent inverse dynamics control, which means that we defined how the system is moving. We then projected the dynamics and this desired acceleration into the null space of the contact constraints and did inverse dynamics with the support consistent formulation. And then the fourth and most powerful formulation that we derived was task space inverse dynamics control, where we were directly regulating in task space by defining a sequence of quadratic problems, a sequence of objectives that have different priorities. We would like to start here with looking at one of our very first prototypes we developed at ETH. This is Alof, walking purely statically, so center of gravity remains always within the support polygon. That means we're shifting the center of gravity, then we're moving one leg, we're moving another leg, we're shifting again the center of gravity. And what is happening is that the main body controller determines the joint angles that need to be sent to the controller and then executes this. So this is pure feed-forward position, position planning and execution. We are looking at this in the form of a small quiz where we do calculate the motion of a complex gate with such a system and then apply either inverse dynamics or inverse kinematic control. If you look at the floating base system of this Alof robot, we have 4 legs. Every leg has 3 degrees of freedom, a knee flexion extension, a hip flexion extension, and a hip adduction and abduction degree of freedom. So 3 degrees of freedom times 4 actuators equals to 12 actuators in total. Plus we have the base, which is free floating. It is connected to the inertial frame through unactuated base. Degrees of freedom, 3 in position and 3 in orientation. If you do static walking, we're moving one leg at a time. We have 3 contacts active and we're moving the 4th leg. So we're indicating here the legs 1 to 3 as stance legs, and we have the fourth leg in swing phase. So that's the problem. Now what we would like to do is we have to first identify how many generalized coordinates that we have, how many base coordinates we have, how many actuated degrees of freedom that we have, and how many contact constraints are active in this situation that I have here on the left when three legs are in ground contact. The second set of questions is then that I would like you to write down the contact constraints. Then I ask you how many degrees of freedom remain controllable if these contact constraints are satisfied. And then the seventh one is like which degrees of freedom remain controllable. So what can you still do with this machine while ensuring that these 3 feet remain in ground contact? And the third batch of questions is I give you now a desired swing velocity, and so that means for that point a velocity, so that velocity, the desired velocity of this fourth foot point with respect to the origin in world fixed frame. And I want you to tell me what is the generalized velocity of the complete robot. Then you have to tell me whether this is unique, it's the only solution that we can achieve. And the last one is then if it's still possible to follow the desired swing trajectory without actually moving the joints of the fourth leg. So can I follow a predefined trajectory here while these 3 joints here are locked? Then in the next set of questions, what we're looking at is the following situation. We have 2 tasks we look at. First task is that we want to move the foot. That's task 1. So we want to move this position of that foot 4. And the second task 2 is that we want to have the base position orientation constant. So the base here should not move at all. So what I would like you to do is to write down the solution for case A and case B. So when we have these 2 tasks given through the Jacobians and the objective you want to achieve, what is the solution if I'm formulating this as single task optimization? What is the solution if I formulate this as multiple tasks? Then I want you to write down what is the difference between these 2 formulations and what happens in a singular configuration. So assume that this leg is fully stretched out. What happens then? So write what is J1 as a function of the J's we introduced before, write what this W is, and then the solutions for A now and B. This quiz has given us in the end a Q dot desired, a motion plan. So we know how the system is supposed to be moving. Now the classical simple method is that we are now having a very high gain position controller that takes the measured Q and the measured Q dot as well as the planned one, does a PD feedback on it to calculate the joint torque, and with that modifies the robot dynamics. Now this is what we're doing, for example, on the Alof robot, which was a robotic system we developed at ETH about 10 years ago. This is a purely kinematically controlled machine, and what you're seeing in this video is pre-planned trajectories that are blindly executed. So we are planning in joint space and we're executing these joint trajectories. You see the machine is becoming pretty versatile. There's many things we can do. However, we're also limited to environments that are perfectly known to the robot. This can be nicely seen in this video with the little dog, which is a similar robot that executes pre-planned motion trajectories in joint space. But now we have obstacles on the ground which are unknown to the robot. It only executes like feed-forward trajectories in position space. And as you can see, like whenever we hit an unknown obstacle, this robot is prone to tip over and cannot really operate like that. So if you want to have kinematic planning and execution, you really need to know very precisely all the details about your environment and carefully plan for that. An alternative approach to this is that instead of having this high gain feedback control on position space, So having here very high gains, one can think of lowering here the gains. So making the system much more compliant. That means if you have an obstacle, these obstacles will disturb your planned motion, but the change in torque is not that big, so we can still operate the machine. However, as we have seen in the earlier classes, this requires some sort of a model-based compensation. And this we do typically through inverse dynamics control. So we are calculating a feed-forward compensation, which is the support consistent dynamics, the inverse of that. So we're taking an inverse dynamics of a support consistent description to calculate the feed-forward torque, and we add the feedback torque, but now with much lower gains. And if you do that, you can play the same experiments as we were doing before with a little log, and all of a sudden this machine can really cope with unknown obstacles. So instead of just like rigidly sticking to the kinematically planned trajectory, here we do the model-based compensation, and the plan is not followed that rigidly anymore, and hence it can walk across this unknown terrain. Now this concludes the first part, the kinematic control and the low gain impedance control in joint space together with inverse dynamics compensation. We move on now with the two formulations for support consistent inverse dynamics control, and then finally end up with the task space inverse dynamics control. For support consistent inverse dynamic control, what we need to do first is we have to find the desired acceleration and then do inverse dynamics with this desired acceleration such that everything remains consistent to the supports. In order to find the desired acceleration, what we have to do is we have to bring together all the different tasks that need to be fulfilled. First task is here, we want to follow a desired swing leg. We formulate this in as a task in acceleration, so that the acceleration of that foot is the Jacobian times the q double dot, and again, like we have a floating base, but I write here q double dot is just for laziness, plus j dot q dot, and that must be equal to the desired acceleration at that foot point, which is a feed forward acceleration plus a feedback on the position offset and velocity offset at this point that we are tracking. Then we want to move the base along this red line. Also here a high-level planner has given us a target base configuration and motion and position. So we move the base. Here we have this w dot of the base, which is the j base times q double dot plus j dot q dot, which is equal to the desired acceleration at the base, which is composed of a planned acceleration plus a feedback part on the position and on the velocity. And on the position, we have to again remember we have the linear position offset, which is straightforward, but then for the rotational error, we have to be careful in how we are taking this. Then we have to ensure ground contact constraint. So these red feet here, they are not moving, which means the acceleration and the velocity have to be 0 at this point. So we set the acceleration at the contact point to be 0, and that gives us in the end a completely defined motion of the system. So we have 3 degrees of freedom that we're defining here, we have 6 that we're defining here, and we have 3 times 3 equal to 9 that we're defining here. So in total we have 18 degrees of freedom that we have to control, and we have these 18 degrees of freedom that we are defining in the motion here on top. So what we can do is we can then simply stack these individual tasks we want to achieve, and again, since we have no redundancy and if you're not in a singular configuration, this matrix here is then a 18 by 18 matrix, so it can be inverted, and that means we can directly calculate the desired acceleration of the complete robot, and then we can use this in order to do inverse dynamics. And remember, if we have more tasks. We might have a pseudo inversion here. We can also do prioritized inverse kinematics to get this desired acceleration. That means we have highest priority to contacts. We maybe have second highest priority to the base because stability is more important than tracking, and then we have the lowest priority to moving the swing leg along the predefined trajectory. And then we do inverse dynamics control. So we take this desired acceleration, we inject it into our support consistent dynamics, and since we do this projection with the support null space projector matrix, we get rid of the contact forces, so we have this independent of the contact force, and we can directly calculate the joint level torques. The second control method that we're looking at is at task space control as a quadratic program. This slide is more or less a recap of what we have heard 2 weeks ago. Still, I think this is so important that I want to retake it here. So what we're doing is we're trying to optimize for x, and x is the stacked vector of acceleration, the type we're moving, the motion of the system, then the contact forces we're having, and the joint torques we need to apply for it. And we have to formulate now all the different constraints and objectives as a least square problem. That means the dynamics equations of motion for a floating wave system, which includes these contact forces and which includes the selection matrix that makes the base unactuated. This is reformulated with an A matrix equals to this M, the contact Jacobi transposed, and minus S transposed, and the B vector. And if you insert the X in here, you get essentially this equation here on the left hand side. Now obviously this is an equality constraint, it has to hold, so this optimization objective has to be fulfilled with highest priority. However, as we know, we have a non-unique solution in here, so we can trade off different torque distribution with different ground contact force distribution, and depending on how well we define the motion, we can also trade off with the motion. Then we have motion tasks. Same here. We transfer this into an A matrix and a B vector. Same for force tasks, and same for objectives that we have in tau. And then we give all these A matrices, we give them a different priority level. This is now all with equality tasks. We didn't bring in here inequality tasks, but if you have a sophisticated quadratic program solver with equality and inequality constraints, you can also bring in very nicely inequality constraints. So what we do then is we write this locomotion as a multitask optimization problem. Step 1, we optimize the motion while ensuring that the equations of motion is satisfied and ensuring the contact constraint. So these two things always have highest priority. If they're violated, we have an inconsistency in the formulation. And then we have also other hard constraints, namely that you have to have a positive ground reaction force in vertical direction, that you have to stay within friction cone, otherwise you would slip away. Now this can be always fulfilled, these two things, right? There is no way that this is not fulfillable, but you can always compromise on the motion. Then step 2 is you want to now also, for example, swing a leg. That means you add an additional objective for moving the leg such that the same constraints hold as we have here above, but additionally we say that this higher priority task is not influenced, so the costs that we have achieved in this optimization up here is not changing. So we're not compromising more on that task. in most of the time these priorities and the way we're formulating the task is selected the way that this C1 is 0. And then as a last step, we are minimizing, for example, the torque, or we're minimizing the total force to get an equal force distribution, or we're minimizing the tangential force. But all of that only subject to all these higher level elements are fulfilled. And we're going to see in the case study next week in how all of that comes together in a complex formulation for like doing a locomotion maneuver or a locomotion interaction maneuver. For tomorrow's exercise, we are applying this formulation to the earlier spot version. This is like one of the very first prototypes where we have a rudimentary kinematic model, and we are formulating multiple objectives for how the base is moving, how the end effector is moving, how ground contact constraints have to be satisfied with the environment to achieve motions like this. So here, for example, the end effector stays at the same place while the base is moving, or you're keeping the base a certain place while you're operating at the end effector, and so on and so forth.